some summary statistics for measuring large-scale structure beyond two-point correlation functions. When I submitted my abstract, I was a little bit overly optimistic about how much progress I would make on it this summer. So I've shifted my talk to talk more about work I've been doing within DES with many great collaborators, including some here. All right. So if I'm going to talk about how we can use galaxy surveys like DES to test our understanding of the behavior of gravity on cosmological scales. And so I think to do that, I think it's worth talking a little bit about, make some framing thoughts about how we approach cosmological tests of general relativity. And for that, I want to emphasize that general relativity as a description of gravity is one component of our standard cosmological model, which we generally refer to as lambda CDM. The other ingredients include this description of the composition of the universe being made up of dark energy and dark matter, cold dark matter, cosmological constant dark energy being part of lambda CDM. This often implies flat geometry and some specific properties of initial perturbations from, for example, a theory of inflation. So the goal of, I would say, most of cosmology experimental efforts is to use observations of the large-scale universe to constrain this model. And that's generally done in sort of two broad ways, well, many ways, but I'm going to split them into two broad ways. One is you can look at how these ingredients, what implications they make about the expansion history of the universe, as well as the evolution of fluctuations in density and structure within that background. And so by analyzing observables associated with these two things, we can compare our measurements to the predictions of our model and look for gaps where this simplest lambda CDM model doesn't quite match observations, and hopefully that'll give us some clues to develop a more fundamental understanding of most of the pieces of this model, so dark energy, dark matter, et cetera. When we think about ways that we might want to test whether general relativity needs to be extended on cosmological scales, the motivations for looking at that are tied, can be tied to our desire to understand what dark energy is, what is causing cosmic acceleration. So, you know, as I'm sure we're all familiar, Einstein's equation describes the relationship between the curvature of space-time and the matter and energy in it. And there's some freedom to, you know, move stuff from one side of this equation to the other and redefine fields. So there's some ambiguity in defining what counts as a dark energy, what counts as modified gravity. There are people who have much more expertise in this than me that might make different distinctions. But, you know, one of the things you can ask when we're trying to understand dark energy is whether the accelerating expansion of the universe could be a sign that general relativity needs to be extended in some way. More conservatively, you can also ask, by looking at models which extend general relativity and constraining them, we can look at where general relativity and what properties of gravity have been really well tested and constrained. So what deviations are still allowed given observations. And if we're looking at ways to extend our description of gravity, there are many possible ways to do this. So this is a slide by Tessa Baker that is fairly busy, but just kind of is meant to show that there's a lot of approaches you can take that if you want to go beyond Einstein's equation in describing gravity. And I'm sure that mainly to just advertise that there's a big model space out there to explore. And you know, if you have a favorite one of these models, so different people will make arguments for some of these models or others being more theoretically well-motivated or stable or interesting to look at for various reasons. You could go and take your favorite model and do the very hard work to go all the way from, you know, your Lagrangian or something that you could write down to your observables and get some insight of how that specific model is constrained. The thing is, there's this big model space of possible ways to change our description of gravity. There's not like one or even a couple most favored of these models. So there's a big model space, and so it's not particularly feasible to go through and check everything, or at least that's a very big, that would be a very sort of expensive effort in time and computing power. And so I like to think of approaches to testing general relativity and just in general our standard cosmological model, the lambda CDM picture, sort of on a continuum from sort of more theoretical approaches to parameterizing deviations from GR to more phenomenological ends. And sort of on the most phenomenological end, I would put these tests where we look for tensions between experiments. So you can constrain lambda CDM parameters using different observables. For example, this is a plot I'll show slightly bigger in a slide or two, or a few, of sigma 8 or S8 constraints on the amplitude of matter density fluctuations in the universe from the CMB and from lower redshift large-scale structure measurements. And sort of in the middle, you can array a lot of different ways that people parameterize changes to gravity. If you're generous, you could put a lot of different lambda CDM extensions sort of on the more phenomenological end. You add parameters if gravity changes and you're trying to fit a WCDM, like a dynamic dark energy model, depending on where the changes to Einstein's equation show up, that you might pick that up in your WCDM parameters, even if that's not explicitly designed for changes to gravity. If you want to be more on the theoretical end, you can try, but you don't want to have to take every specific formulation of a model and go all the way to observables. You can look for more general models. So this is where people look at EFT of dark energy models or the Horn-Deskey gravity, very like general descriptions of beyond GR models you can write down. The challenge there comes with that these general models end up having a lot of degrees of freedom that are frankly so many that it's very difficult to be able to constrain all the parameters you end up with, and specifically, which is going to be kind of my focus of a lot of this talk, is to constrain them robustly and make sure that you're not confusing some astrophysical or modeling uncertainty for new physics. So for this talk and for the types of constraints that I'm going to be talking about, we're very much on the phenomenological end of things. We're introducing parameters that can look for certain physical effects that could come from changing gravity, but could come from potentially other things, and trying to get a good handle on what we can say and what we can't say with our available data. Okay. So given that context, I'm going to talk through an approach to constraining deviations from GR, these very phenomenological model extensions, with dark energy survey data. So I'm going to spend a little bit of time introducing the analysis we do with DES, combining galaxy clustering and weak lensing measurements, and then I'll talk through some of the ways that we can use those measurements to constrain gravity. Okay, so some of these slides will be familiar to people that were at Cosmo last week, but just as there were a lot of talks, so it's good to give another overview. So DES is specifically an imaging survey, or sometimes we say a photometric survey. So that means in contrast to pointing like an optical fiber at each galaxy and getting a really good redshift measurement, we're taking images of the sky with a giant digital camera on a telescope. So that means that we can observe a lot of galaxies and we can get information about their shapes. But a downside of that is that rather than having good spectra, which would give very precise redshift measurements, we have to try and infer their redshifts by looking at how the spectra of different galaxies, so this is an example showing an elliptical galaxy at different redshifts, so the spectra with the black lines. We look at how those spectra show up in different color filters, which DES has GR, IZ, Y. And so we have to infer redshifts from that. So we generally have pretty uncertain redshift measurements. And so rather than making three-dimensional measurements, we split the galaxies into redshift bins, so tomographic bins, and make measurements based on that to get some three-dimensional information about the evolution over time in the universe. DES completed observing in 2019. There were 6 years of observations for a total of about 750 nights of observing. There have been over 700 people involved in DES, including many from Brazil. And that data taking, there's sort of two main surveys in that. So there's the wide survey, which is a 5,000 square degree footprint, so that's 1/8 of the total sky. And then there's a separate supernova survey where certain patches of the sky were revisited at a more frequent cadence to look for transients. So DES by design, I'm going to be talking about one specific analysis measuring galaxy clustering and weak lensing, but it's designed to be a multi-purpose project. So there's a lot of different kinds of science that one can do with this data set. There's analysis looking at, in addition to the galaxy clustering and weak lensing, galaxy clusters, supernova. There's people studying Milky Way structure and dwarf galaxies, quasars, strong lensing, and solar system science, so a bunch of other things. So I'm focusing on galaxy clustering and weak lensing, but it's in general, a really rich data set that gives people a lot of science to play with. Okay, so the status of DES, as I said, the data taking is completed, and we've been analyzing the data in chunks, and so currently the cosmology results that are out and that I'm going to be telling you about are based on the first 3 years of DES data. And so that data covers the full 5,000 square degree footprint at about half the final depth. So we revisit each direction on the sky a certain number of times to be able to average out some noise. So the year 3 data includes half of those visits. And we are ramping up the year 6 analysis to do the final analysis of this DES data now. And yeah, this is just an image of the DES footprint on the sky. It's kind of a funny shape, but the thing here is there's a big circle that's looking out of the southern pole of our galaxy. So the plane of the galaxy kind of goes around here. And then there's some rectangles added on to increase overlap with other surveys. So this rectangle at the bottom is here to overlap with the SPT, the South Pole Telescope CMB experiment, so to facilitate like cross-correlation experiments that can be done with those. All right. So the analysis I'm going to be talking to you today about is the galaxy clustering and weak lensing experiment, to just walk through a little bit about what those measurements look like with this cartoon. So we look out at the universe. What our theory modeling gives us is a way to predict the statistics of the total amount of matter, so the underlying dark matter. We don't see the dark matter, rather we see the galaxies living in overdensities. And we can probe the large-scale structure in one way by looking at how, when a sample of distant source galaxies in yellow, and their light travels through the large-scale structure, weak gravitational lensing introduces some very small distortions to their shape. It's only about a 0.1% distortion. But if we observe enough galaxies, we can look for the correlations in galaxy shapes as a function of their angular separation on the sky to get a signal that depends on the overall clustering of the dark matter causing that lensing. So we call that's the cosmic shear or weak lensing measurement. We can also look at another sample of foreground galaxies, which we call lens galaxies, and use the fact that they tend to, they appear in the overdensities causing that lensing. And so the galaxies themselves are a bias tracer of the underlying dark matter, so we can make a correlation of the positions of these lens galaxies for the galaxy clustering measurement. And that'll also be roughly proportional to the clustering of matter with an unknown bias factor relating the distribution of galaxies to the underlying distribution of dark matter. And then given these two tracers, we can look at the cross-correlation between the two, so the positions of the foreground lens galaxies and the shape distortions of the background source galaxies. And so here we end up with 3 different kinds of 2-point correlation functions. And so the jargon that we use to refer to this combined analysis is the 3-cross-2-point analysis, because there are 3 different 2-point functions, 2-point angular correlations. All right. And it's a benefit of using these things together is that they have different kinds of uncertainties and different dependence on astrophysical uncertainties like galaxy bias parameters, for example. Okay. So this is what the measurements look like for the cosmic shear 2-point function. There are a lot of subplots here, and the thing is here, as I mentioned, we divide the galaxies into different redshift bins. So each of these subplots are different correlations between the galaxy shapes in the different bins along the line of sight. There are sort of 2 sets of triangle plots here, the upper and lower. That's because cosmic shear, the weak lensing, the shape distortion is a vector quantity on the sky. So it's a 2-dimensional quantity, which means you can decompose it into 2 degrees of freedom. So these 2 measurements are that signal in a decomposition of the shear. The data points are the measurements from our DES Year 3 analysis, and the solid lines are the best fit model predictions for these 2-point functions. So it's by doing the comparison of the model prediction to the data points that allows us to constrain parameters of our theory. So we can look at how changing different cosmological parameters affects the agreement between the measurement and model, and that's where we get physics information. The one last thing I want to highlight here is that in all of these subplots, there's some gray shaded regions. Those are scale cuts, so that denotes regions where we do measure data points, but we don't actually use them in our parameter inference, and that's because those are, so they're all at small angular scales here. So at the smaller angular scales are modeling uncertainties related to nonlinear galaxy bias, as well as the impact of baryonic physics, so AGN, supernova, et cetera, on the clustering of matter. So we don't trust our model enough to be sure that our assumptions there wouldn't bias our cosmology results. So we just leave those points out of our analysis. All right, so that's the cosmic shear measurements. Here are the other 2-point measurements that we use. So for our weak lensing sources, we have 4 redshift bins. For the lenses, which is a specific sample called the Maglim galaxy sample, we measured it for 6 bins, but we ended up only using the 4 lowest redshift bins in our analysis because we found some evidence that these highest redshift bins seem to be contaminated by some observational systematics related to the photometry, we think. So we're working on understanding that a bit better. Again, to go from the measurements to parameter constraints, we do a Bayesian analysis that's built on comparisons of the measurements to a model. So here, D for data is the collection of all those data points I showed you on the last couple slides. M is the model predictions for that. We compare them using a Gaussian covariance, which is shown in the upper part of the triangle here. So it's analytically computed. What this plot shows is basically each pixel row corresponds to one of those 460-ish data points that I showed you on the last couple slides, and the color marks how much you expect from those data points to covary with each other, just given different realizations of the large-scale structure. We fit this in our lambda CDM analysis, we fit this with a 31-parameter model that includes 6 cosmology parameters, including neutrino mass, which is a choice that differs a little bit from DES from a number of other cosmology analyses where sometimes you tend to fix neutrino mass. And then we have 25 additional parameters that encompass some astrophysical and modeling uncertainties and measurement uncertainties. So we marginalize over those nuisance parameters to make sure we're not biasing our cosmology results. Okay, so that's the setup. That's sort of the general overview of what we're doing when we do this galaxy clustering and weak lensing analysis. Now, let's use that to test our understanding of gravity. So, as I mentioned early on, one way that we can test our standard cosmological model, that's sort of the first step towards doing this, is to look for tensions and ask whether the constraints we're getting from DES measurements of large-scale structure at redshifts less than about 1, do those constraints agree with what you'd expect given measurements from the cosmic microwave background and extrapolated forward with lambda CDM. And so this both plots here are showing S8, which is a measure of the amplitude of density fluctuations at redshift 0. And this is highlighting the sort of much talked about S8 tension, where when you constrain S8 using the CMB primary anisotropy information, you get you expect a higher value of S8 than what we seem to observe with a number of different weak lensing and galaxy clustering measurements. So the one that comes out of the DES Year 3 analysis from lambda CDM are in these bottom 2 green points. And for our measurement alone, statistically speaking, when you look at different measurements of assessing tensions between these green points and this yellow one, we don't find a super statistically significant tension. Just looking at the S8 parameter, we're only about 1.5 sigma off. When we look at the full parameter space using some Bayesian statistical metrics, it gets a bit lower. But one could still argue that it is still intriguing that this collection of all these different measurements tend to be low. So it's quite an involved process to combine these different measurements, and there are teams working on doing that. But if you kind of maybe somewhat irresponsibly chi by eye, you might have a stronger significance if you were to combine all of these low redshift data. So not definitive, but definitely intriguing. And given how well lambda CDM performs in a lot of different contexts, we want to make sure we understand this well. And so I'm going to take this occasion to illustrate how do we think about this with a cartoon that we made for some outreach stuff online with DES. But so we're trying to learn about fundamental physics by comparing measurements from different observables in the universe. If we find a tension between these observables, we have a couple next steps. And the first two are maybe somewhat obvious. We want to work towards making even more precise measurements. So if we can tighten our constraints, a 1.5 sigma offset, if the center of that parameter constraint stays and the error bars tighten, it can get more significant and help convince you whether or not that's real or a statistical fluctuation. As I said, we're working towards our final DES analysis, and also these kind of analysis from DES and other current surveys can also be seen as a test bed for developing techniques and methodology that we'll need for next generation surveys like Euclid or LSST, which will be able to get us to an even greater precision. We also really want to make sure that we understand different modeling uncertainties, and so this is a place where work between different collaborations, so for example, between DES and KIDS, which is another current weak lensing survey, become really important. And just a lot of validation and just making sure you understand how your constraints respond to different contaminations and things that you might expect to affect your data. And then additionally, which is where the rest of the talk will come in, is you can explore what kinds of physics, if this tension is real, could explain that offset. And so you can ask what kind of physics could generate this sigma 8 offset. And then you can additionally ask, are there kinds of new physics that would give us a signal that we can find that maybe just looking at these tensions isn't that sensitive to? And so that kind of framing is the goal of our project, which results just came out about a month ago. So within DES, we've had an analysis team working to extend the galaxy clustering and weak lensing analysis to a number of models beyond lambda CDM. And so this is showcasing some of the people that have been involved in that analysis. The models that we constrain include time-dependent dark energy of state. We looked at non-zero spatial curvature. The ones that I'm going to highlight in the remainder of the talk are a modified gravity parameterization and then a phenomenological test where we constrain sigma 8 in different redshift bins. And we also studied sterile neutrinos, which I won't talk about now, but I find pretty exciting as well. So that's another thing that I'm happy to be asked about during coffee breaks. Yeah, so I co-led this team with Agnes Ferte, who just moved from JPL to Slack. And as I said, we released our results into the archive just last month. The very short summary of the paper is we tested all these models. We didn't find any significant deviations from lambda CDM, but we did a lot of work on the methodology and validation to back that up, and there are a couple of things to highlight associated with that. And yeah, we have public data online, so the data vectors, the covariants, they're all on the DES data release website. We've also shared most of the MCMC chains that we use to run this, so they're available to play with if that's something people are interested in. Okay, so as I said, I'm going to mostly focus on the modified gravity sort of adjacent models we looked at, but this is just to highlight one of the results from our analysis that is from time-dependent dark energy. And so this is when you allow the dark energy equation of state not only to be different from -1, but to have some time dependence. And you can constrain these two parameters, W0 and WA. And we looked at that. So these two plots are from the same constraint, just the right one is zoomed in a bit and showing different combinations of the data. And the thing I was going to highlight here is that the green dashed line here is from measurements from EBOS, BAO, and RSD plus Pantheon supernova. And the BAO and supernova measurements are geometric measurements basically designed, and they're powerful because they really probe the expansion history of the universe very well. And so for models like dark energy equation of state, if you're looking at combined constraints, including the BAO and supernova data, a lot of the constraining power is coming from those geometric measurements. So adding DES to those, which is shown in the purple, or adding Planck to those, which is shown in the pink, or adding everything together is in black, you can move the results around a lot, but you're already, just from the BAO supernova, getting most of the constraining power there. So looking at this with DES and other galaxy surveys is important because it allows you to check the redundancy of your measurement, check the consistency. But the place where DES and other lensing surveys like it can really add a lot of information is when, rather than changing just the background expansion history, you're changing the evolution of structure growth. And so I was saying, looking for tensions is approach 1 to testing gravity with experiments like DES. Approach 2 is picking a specific parameterization and constraining it. So the way we do that in this paper is using this sigma mu parameterization. So this is already on that sort of flow chart I showed at the beginning of the talk. This is a specific parameterization of modified gravity, but I will emphasize that it is very phenomenological. It's not tied to some underlying Lagrangian changing Einstein's equation. What it does is you introduce a couple generic functions which modify your Poisson equation. So mu changes the Newtonian potential, so the gravitational potential experienced by massive particles, while sigma changes the gravitational potential seen by massless particles, so it changes the lensing potential. There's different ways of defining these parameters. So if you've seen people talk about the gravitational slip, that you can use that instead of sigma or mu, but this is the way of formulating changes to the Poisson equation that we're most sensitive to, so this is what we use. So these could be generic functions. They could have some dependence on both time and scale, length scale. For our analysis, or at least for this initial analysis, we make specific choices there. So we assume that both of these functions are scale independent, so there's no k dependence. And we assume a specific redshift dependence. So we assume that they sort of turn on at the time of the accelerating expansion in the universe. This is a somewhat arbitrary choice chosen because we're interested in accelerating expansion. There's a lot of different approaches to do this. There's also ways of doing similar changes to your modeling that are more motivated by specific models of modified gravity, for example, F of R gravity. And there is work within DES led by Agnes and some other people who did a lot of the modified gravity modeling developments to extend this analysis to look at more modified gravity constraints. So that's something to keep an eye out for going into this fall. But yeah, within this initial release of Beyond Lambda CDM results, we constrain this particular parameterization. And you can see that DES in blue here is sensitive really to a product of sigma naught and S8. So we can't, on our own, distinguish between how clumpy matter is and how much the clumps of matter are driving the strength of the lensing. And so here you can see that it becomes really important as we add this modeling freedom that combining with other probes of structure growth. So here the constraint on S8 in the green contour is coming mainly from the redshift space distortion measurements that are from the EBOS collaboration. And the fact that the redshift space distortion measurements that aren't sensitive at all to sigma naught, but they are sensitive to S8 and mu naught, allows us to break degeneracies and really pin these down. There's some funny behavior from the Planck contours. The fact that these red contours are a little bit offset in sigma is related to the lensing amplitude tension, which Valerio mentioned in his talk, that the temperature and polarization power spectrum Planck have a little more lensing smoothing than you'd expect given the other constraints on cosmological parameters. But we find when we combine everything together in black, our constraints on sigma naught and mu naught shift right on top of 0 and 0, which is the values associated with general relativity. So here, maybe other than something funny going on with the CMB, we're not seeing a preference for any deviations from general relativity. So along with this model, I'm going to talk a little bit about some of the challenges that come with this. One is to note that this kind of parameterization is really only defined for when you were describing linear density fluctuations. So while you can try to use it for nonlinear fluctuations, exactly what these functions are doing, you have to make some fairly arbitrary choices. That's kind of in the prior experimenter's preference. For our approach, because they're really only defined well for linear fluctuations, we opted to make even more conservative scale cuts than from the lambda CDM analysis. So rather than just cutting out scales where we're worried about baryonic physics, we also cut basically any scales where nonlinear corrections to the matter power spectrum matter. So we lose a lot of data points, and at this point, this is really a limiting factor to the constraining power with this blue contour. Yes?
Just a quick question. How many nuisance parameters you have in this analysis?
25.
The same 25?
Yeah, so it's the same as the lambda CDM analysis, just with these two extra parameters. Or there's 22. We changed to a simpler intrinsic alignment model so we make some simplifying assumptions on a couple of the cases. Yeah, so the fact that we cut to linear-only scales, one of the signs that this is one of our limiting factors is that when we compare our DES year 3 constraints from this 3x 2-point measurement alone to the year 1 constraints, they're really comparable. We're not gaining constraining power, and it's because we're having to throw away so much of our data vector. So that's one of the big motivations behind this sort of looking closer at different modified gravity parameterizations and pushing that would let us push to smaller scales and keep more of our signal to noise. And that is something that, as data get more precise, that'll only help us make new physics inferences if we can actually take advantage of that precision in our analysis. All right, so I just want to spend a couple minutes talking about baryon feedback as an example of something that we need to worry about. So say we come up with a modified gravity parameterization that we don't have to cut to linear-only scales. Then we're back to the scale cuts we defined for lambda CDM, which are one of the main motivations is avoiding baryon feedback. So this is a challenge even in lambda CDM. So the presence of baryonic processes, AGN, et cetera, can impact how matter clusters on small scales. And we can get a handle of the size and what that kind of effect looks like by looking at studies done on hydrodynamic simulations. And so what this plot here is the lines show the ratio between the hydro simulation power spectrum accounting for baryon effects over the dark matter only ones for a number of different hydrodynamic simulations. So you can see that there's some similarity in different shapes, but there's a lot of variations in how much of a change to the power spectrum you expect from these baryonic effects. And that has to do with different ways that these simulations implement the feedback and impacts, which is definitely out of my expertise. But the thing to note is that there's a lot of variation in how big you expect this effect to be. So there's a lot of modeling uncertainty there. So there are ways that you could parameterize and try and marginalize over these effects, and people have done some really interesting studies doing that. For example, some DES papers on this are by Huang et al. And Angela Chen had a paper out earlier this year trying to constrain this. There's work being done cross-correlating galaxy clustering and weak lensing with like TSZ and KSZ signals to get a handle on where the gas actually is in the universe. But that's all in a state of development. In year 3 for DES, we determined that sort of the uncertainty introduced in trying to marginalize over these effects and the assumptions you have to make to decide how much of this range you want to marginalize over, et cetera, it was about equivalent to just cutting the scales where you had to worry about this, so we opted to make the scale cuts. And once we made those scale cuts, we could check that our cosmology constraints, for example, on omega matter, and I cut off the label, but this is S8. We could check using analysis of synthetic data vectors, which basically you treat a model prediction for your data as if it is data and analyze it, and you can add effects from the baryons to that and make sure that you have simulated data with baryonic effects. You're analyzing it with a model with no baryonic effects, and you can see how much does that shift your cosmology constraints. And we made sure for these parameters that are sort of the main results of our analysis that the shifts between analyzing a synthetic data vector with no baryons and with baryons shifts our parameters by less than 0.3 sigma. So it's not going to bias our cosmology significantly. And just to highlight, especially because I think some of you know Otavio Alves, our ability to do this quickly for a lot of different kinds of systematics, so baryons being one example of them, we have an important sampling-based method that allows us to do this quickly that Otavio and Noah Weaver-Dick developed. Okay, so this is a challenge even for lambda CDM analyses. And then when you start looking at going beyond lambda CDM, particularly for modified gravity, it becomes even more of a challenge. So presumably, if you change the behavior of gravity, and a lot of these modifications of gravity that people consider that haven't already been ruled out, pick up some environment-dependent effects, so where in dense regions the extensions to the general relativity get screened out and they show up in underdense regions. There's a lot of nonlinear stuff that can happen here, which could plausibly affect baryonic processes and how it feeds back onto matter clustering. So I know there are research groups that are starting to do hydrodynamic simulations with modified gravity in specific models. But given things we have on hand, we don't really have a way of robustly telling how much these sort of arrays of possibilities might change in a given sort of framework for modified gravity. So ideally, if we had one very well-motivated modified gravity model, it would really be worth it to run your hydro simulations, and in the same way that we're working to being able to marginalize over baryonic effects for lambda CDM, to be able to include that as a nuisance parameter or nuisance parameters in your modified gravity constraints. But at least at present, we don't really have tools to do that yet. And so in practice, for our year 3 analysis, and I think what's probably going to need to be the case, at least in the near future for a lot of analyses like this, the thing we can fairly robustly say is we can make sure that if the data is lambda CDM with the systematic that we're not modeling, so here baryon's an example, then we won't get a false detection of modified gravity when it's not there. If we find the detection of modified gravity, there's still some theoretical uncertainty in terms of disentangling these effects. But this is just saying, this is what we in practice do for our analysis for modified gravity and other extensions to lambda CDM. And this is a somewhat busy plot, but just showing the kind of thing we do to check for this. What this is showing are marginalized constraints on our sigma and mu parameters. Baseline means we're analyzing a synthetic data vector that it's produced with the same model we're using for parameter fitting. And then these alt data lines is where we alter the simulated data vector by adding baryonic effects or some other uncertainties and see how much compared to baseline do our constraints shift around when we do these simulated likelihood analyses. And here this is showing that basically you compare the different rows to the top row and see that we don't shift by more than a third of a sigma in any of these cases. So, and yeah, as I said, I'm giving baryons an example here, but when there are a number of our systematics that are mostly well studied in general relativity, and when we start introducing changes to growth rate or the behavior of gravity, you might need to worry about how that might affect intrinsic alignments between galaxies from tidal effects, for example. And so that'll be a challenge here and for other analyses. Yes?
Can you give me an example of what type of modified gravity is being accounted for? I mean, this is supposedly a very low density regime. I mean, expecting something to be affected by the gravity. So what's the physical mechanism? If I imagine something's going to happen there, it would do a heck of a lot in the neutron star. Whereas it also then involve a Bayesian mechanism to shield all that away?
That is a good question. I think, which I am not going to be able to give a good answer. So I would just emphasize this is a very phenomenological model, just saying on the scales that we're sensitive to, how much can we constrain deviations from the Poisson equation? if we find something, or if there's a particular model being studied for impacts on neutron sources, it would be interesting to look into mapping between these two regimes. I'm not deeply familiar with efforts that have been done to do that. Yeah, there's a bit of a lamppost effect here, admittedly. We're like looking for what are deviations from GR that we can constrain well with our data, what can our data say, and the hope is that placing limits on these kind of functions or these type of parameters gives sort of benchmarks for if people are developing modeling or predictions for maybe more fundamentally motivated models to kind of compare, like, we can test for some agreement between the lensing and Newtonian potential, for example, which is, I think, the place where this kind of analysis adds information. Taking a step even more towards the sort of data-driven phenomenological end of things. So the approaches to testing gravity that I talked about, one, tension between different data constraints on lambda CDM. Two is pick a parameterization and do your best to constrain it robustly. And approach 3 here is, I'm going to broadly say, is looking for phenomenological consistency tests. So look for ways you can maybe introduce, either split your data or introduce some free parameters to your model that test the predictions of lambda CDM, maybe without being particularly physically motivated in and of themselves. So there are approaches to doing this. For example, people look at like growth geometry split analysis, where you ask, like, do constraints on expansion history agree with constraints on structure growth? For our year 3 analysis, we do this bin sigma 8 model, where we implement it by, when we compute our linear matter power spectrum, which is one of the inputs for predicting our 2-point correlation functions, we just scale it by a constant amplitude in different redshift bins. So for each of the lens galaxy bins, so the ranges where we have the most information about the clustering of matter, we get a new amplitude parameter. We sample over that along with our 20-something nuisance parameters and other cosmology parameters. And by looking at that, that lets us sort of ask whether the growth rate that we're sensitive to over time, so the evolution of the clustering of matter as a function of redshift, whether that agrees with lambda CDM. So what this plot is showing is the derived constraints on sigma 8 of z as a function of redshift. The bands here are the constraints from the lambda CDM analyses. So blue is from DES alone. Black is from all of our data together. And then the points are when we add this additional freedom in the model. So we can see that in lambda CDM, as we might have expected from the S8 tension discussion, the DES only line is a bit below the everything together line, which is a bit close, which is basically at where the Planck constraints are. When we add the freedom, we see at high redshifts there's a little bit of movement away from the lambda CDM line, but nothing's really that significantly offset. But as with the sigma mu parameterization, I'm going to highlight one of the other systematic uncertainties that we have to worry about, that when we add this kind of sort of arbitrary degrees of freedom to our model, and particularly when we add that many different parameters, we start having to worry about a robustness to how we handle uncertainties in our redshift measurements. So I mentioned that as a photometric survey, we estimate our distances to the galaxies based on how bright they are in 5 different color bands. There's quite a complex process that we get redshift estimates out of that. That's a valiant effort that is like a lot of the work behind getting these results to be what they are. That was driven by a number of my very excellent colleagues. But basically what we end up with is these distributions for each redshift bin of galaxies. We have an estimate for how they're distributed in redshift. And while each individual galaxy redshift isn't measured well, we can do a pretty good job at calibrating sort of the shape and width of these redshift distributions. They're not completely certain, so in our fiducial analysis, we marginalize over some uncertainties. So I'm going to be talking specifically here about the source galaxies, so the ones that we're measuring the shapes, the weak lensing from. And you can this is just a little lensing optics diagram here. You can imagine if you move your source further away or closer to your observer, the amount and the impact of lensing given some mass of a lens will change. And so there's some uncertain, so if you don't know well the distance to your source galaxy, that'll change a bit what you infer about the amount of clustering of matter doing the lensing. So that's just to try and say that estimating these redshifts is important for estimating S8 and cosmology parameters. So in our fiducial analysis, we account for uncertainties by, for each redshift bin, we have one parameter that basically lets this N of Z function shift right and left. And we marginalize over those parameters. Another approach that you could take is maybe a bit more principled, where you can do a statistical analysis of all the color measurements and what's certain about these N of Z distributions, and rather just having one shape that shifts back and forth, you can produce an ensemble of realizations of the set of all of your N of Z functions that might be feasible given your measurements. And those can be challenged, and you could, instead of sampling over these nuisance parameters that shift the distribution back and forth, you could sample over that ensemble of possible N of Z realizations. And in principle, these two approaches should give us the same constraints, or part of the validation for your 3 analysis was making sure that we could use the simpler just mean shift parameters. And we check that by showing that whether we use we call the hyperrank, this many realizations approach, or we use the simpler and faster mean shift approach, it didn't change the S8 constraints from our cosmic shear. It does shift them a little bit for 3x2 by about half a sigma, so that's something that I think for year 6 we're going to be taking a closer look at. But the shifts are fairly small in lambda CDM, particularly for the weak lensing measurements. All right, but then we look at this binned S8 model where we're adding 3 or 4 degrees of freedom that instead of having a smooth growth function over redshift, you have these possible like step functions. You add a lot of degrees of freedom. And the constraints become less robust to how we handle these redshift uncertainties. And I am keeping an eye on the time. So I'll just to say, the bottom line here is that it turns out our DES-only constraints from this bin sigma 8 model are more sensitive than we would like to these redshift uncertainty accounting. So these two approaches don't give the same answer. But it becomes more, robust in at least everything except the lowest redshift bin when we combine with external data, which helps break degeneracies between the geometry of the expansion of the universe and the clustering of matter. So the sort of more general lesson here, I would say, is when you extend your model, especially when you add a lot of degrees of freedom, sort of more general deviations from lambda CDM, you need to be careful about assumptions that go into how you account for like redshift uncertainties, among other things. And then in general, as you add more degrees of freedom, combining redundant data sets becomes even more important or more helpful to your cosmology constraints. And this is my last slide before the conclusion. Just to highlight that one thing that comes in and that we looked at in our analysis, so because DES, we marginalize over neutrino mass as part of our fiducial analysis, it gives us the sort of fun side effect with our results is that we could very easily produce a plot of how different assumptions about your cosmological model influence constraints on neutrino mass. And you can look in the lambda CDM row of this table where the first column is everything except DES, so BAO, CMB, RSD, and the right column is everything together. In lambda CDM, DES basically adds no information to neutrino mass. And that was not surprising to us. We're just marginalized over it to make sure we include that in our theoretical uncertainties. But when you start looking at models which affect structure growth, this is where adding the additional growth information from DES can help break these degeneracies and distinguish between, for example, these modified gravity parameters and neutrino mass, or these bin sigma 8 parameters and neutrino mass. So this could apply for neutrino mass. This could apply for potentially many other things. But yeah, redundant measurements of structure growth are important because structure growth is hard to disentangle from systematic effects. And that, I think, is one of the main takeaway points. But summary is here just to say that, DES, we use galaxy clustering and weak lensing. There's a lot of approaches we can use to test general relativity. as part of our lambda CDM cosmological model, and that when we start looking at extended models, we have to really take a close look at how we handle systematic uncertainties related to both measurements like our redshift distributions or astrophysics like Baryon feedback. And the modeling uncertainties and the scale cuts we need to do to account for that is one of the limiting factors to our constraining power already. So, there's a lot of exciting prospects for future analyses, both from DES and other experiments. We've got a lot of work to do as theorists to keep up with the increasing precisions of that measurement. So I'll end there. Thank you for listening.
Thank you, Jesse. So, yeah, I got questions from this side.
So regarding the sigma 8 binning model, so in that way, when you run your MCMC, you're allowed for arbitrary steps, and nature should be continuous. So perhaps using some spline with nodes, and are you thinking about that?
Yeah, I think if we update this for a future analysis, and we're looking at, we're working on constraining this with looking at DES cross CMB lensing, in particular because I'm kind of intrigued by this data point at high redshift being a little higher, and there's some other analyses using other kinds of data, which have also seen a sort of similar, like, one sigma-ish hint of maybe there being a little more structure at high redshift. And so, yeah, we want to do future iterations of this, and I think we're going to update it instead of being steep step functions to being some smooth model. And I kind of mentioned over lunch was one of the things that comes in is when you introduce these sort of steps or effectively like shells in density, you can get that will produce redshift space distortion effects because you're introducing sort of steep changes in your linear structure growth. The growth factor gets steps, and so the growth rate gets spikes. And that will have some implications for even our projected measurements, so we had to do some fiddling to account for that. And yeah, so smoothing the model that we used to introduce this will allow us to have that be less like delta function-y and better behaved. So I think that'll be something we're looking into.
Ricardo is also going to get some questions from that side. Any further questions? Okay. Oh, Jesse will be around for a couple of days. So, yeah, so let's thank Jesse again for this nice talk. And